All right, guys, so the test Thursday is going to cover several things. Number one, forces. So we've had a couple of quizzes on forces. It's going to be the same kind of stuff. Most of you are pretty good on the force stuff. But in addition to the force stuff, it's going to have questions about work, energy, and power. And in addition to that, the simple harmonic motion stuff that we started in the last couple of classes about springs and pendulums. I'm going to allow you to use your AP formula sheet on this test. So if you don't have the copy, I will have some more copies available. And for most tests from here on out, I'm going to let you use that sheet. Because, like I said, I just found out you get to use it on every part of the AP, man, so you might as well become familiar with it. So I'll let you use that on the test. First thing I'm going to do, though, is show you a little video about, two little video clips actually, about simple harmonic motion. And those of you who are about to be watching this on video, I will put the URL up at the end of my video for the two videos I'm about to show. So, I'm going to pause this now. It is now. All right, so you guys watching this on video, we're talking about simple harmonic motion, or sometimes it might be called periodic motion or vibrational motion. But essentially, it's simple harmonic motion. Number one, if there's a restoring force that always tries to pull the object back to equilibrium, that restoring force is always in the opposite direction of the displacement. And the size of the restoring force has to be proportional to the displacement. Bigger displacement, bigger restoring force. Smaller displacement, smaller restoring force. The two most common examples in physics that you're going to talk about with simple harmonic motion are a mass on a spring, and it can be a vertical setup, or it can be horizontal. And you're also going to hear pendulums talked about. So those are the two kinds of examples we're going to concentrate on. Masses with springs attached to them, and pendulums. Some important terms to think about: period and amplitude. When we're talking about period, what is the period of something? You guys out in the room here, what's the period? Say again? Yeah, it's not so much how often, it's the time it takes for an object to do what? One cycle. So if it was a pendulum, it's the time it takes from where it started to go to the other side and come back. Okay? One cycle. That's the period. So it's going to be measured in seconds. Now, actually what he just said was the definition of what? What's how often something repeats? What's that called? That's called the frequency. The frequency is how many cycles you get in each unit of time. And there's an important equation. It's on your formula sheet. You all should know it. Big T is what we call period, the time for one cycle. That's equal to the inverse of the frequency. So we could write it that way, or we could just as easily write it that way. So if you know either one of those, it's easy to find the other one. Just put it under one. Another thing we'll mention is amplitude. What's amplitude? If you're talking about like a sound wave, what's the amplitude of the sound wave? Yeah, if this was a wave, here's the equilibrium position. The amplitude is the distance from equilibrium, the displacement from equilibrium. So that would be the amplitude. That could also be the amplitude. That could be the amplitude. So essentially, amplitude is the displacement away from the equilibrium position. So those two words, or those three words rather, will get used when we're talking about simple harmonic motion. Period, the time for one unit. Frequency, how many cycles for each second. And amplitude, the displacement away from the equilibrium position. Those three words will show up. Like we said before, we're going to talk about two main setups: blocks on a spring, pendulums. The video we just watched was about Hooke's Law. And essentially Hooke's Law is about simple harmonic motion. That when you have an elastic object and you pull it away from equilibrium, there's a force that wants to put it back to that equilibrium position. And like we saw in that last video, the formula that Hooke came up with is that the restoring force is equal to negative K times X, where K is the spring constant. It's a measure of the stiffness or not stiffness of a spring. X is the displacement, and F is the force that's trying to get that thing back to the equilibrium position. And don't let that negative sign convince you, or confuse you rather. Not convince you, I don't know what it would convince you of. But don't let it confuse you. The negative just means that the restoring force is in the opposite direction of what? Help me out. The displacement. So if you pull the spring down, the restoring force is up. That's all the negative means. That's Hooke's Law. All right, now this diagram is a good one. And this, if you understand this diagram, you know most of what you need to know about simple harmonic motion. Let's say that right here, in this position, what position might we call that? That's equilibrium. The spring is just sitting there. At equilibrium, what they're calling S here, we've been calling X. What does S mean here? Displacement. I'm going to turn off the light so you can see the diagram better. Not the greatest diagram. So at equilibrium, the displacement's 0. We'll come back to the rest of this in a minute. So now let's say that the mass drops down to this position. What can we say there about the displacement? It's as far down as it can go. So it has a downward displacement, and the displacement is at a what? Max. I'm going to call that X max, maximum displacement. At that point, what just happened to the speed of movement, the velocity? What happened to the velocity at the bottom here? It stops for a moment, right? So we're going to say the velocity is 0. But what's also happening at this instant? It's about to get yanked back up, right? So at this point, our acceleration is going to be a maximum, and it's going to be up. Now, as it goes up, the displacement goes down, right? Which means what happens to the restoring force since they're proportional? Displacement goes down, restoring force goes down, right? As the restoring force goes down, what happens to the acceleration? It goes down, because the restoring force is the net force. Everybody with me on that? So as you get closer and closer to equilibrium, the acceleration begins to drop. Until eventually, when you get back to equilibrium, here the displacement is 0. What's the acceleration at equilibrium? The acceleration, remember, we're at equilibrium, there's no displacement. If there's no displacement, there can be no what? No acceleration, because there's no what? What's proportional to the displacement? The force. So at this point, at equilibrium, the acceleration is 0 because the restoring force is 0. But what has been happening between right here and right here? It's been accelerating the whole time, right? Which means when it gets back to equilibrium, how fast is it going? As fast as it can. So at the equilibrium position, the velocity is at a max. Does that make sense? Now let's say it continues to go on up. Continues to go on up. So as it's going up, what's the restoring force doing? As it's moving up, the restoring force is acting which way? Down. They're opposite, right? So this thing was going really fast, right? It was going really fast from here to here. But as it's going up, since the net force is down, what starts to happen to the speed? It starts to slow down, and it starts to accelerate. So the velocity is up, but the acceleration is down. until eventually it gets up here, and what happens to the speed at this maximum displacement? It stops. So up here at this highest point, the displacement is at a max. The velocity is at 0. And once it stops, now which way is the acceleration going to go? Now it's going to go back down this way, right? Once it stops, the acceleration is going to go back to being a max, but down. Because now the restoring force is going to be pushing in that direction. Does that make sense? Now, in a fictional physics world, that process would continue forever. But we know in the real world it doesn't continue forever, because what stops it? Heat. Yeah, the friction in the spring and the drag between the object and the air eventually turns some of that energy from kinetic or potential into what? Heat, and it eventually stops. That's simple harmonic motion. Let's go through a couple of things one more time, just to make sure you got it. All right, so at equilibrium, this thing's still moving, but it's instantaneously here at equilibrium. Remember, its displacement is 0. It's at equilibrium. It's at its equilibrium position. But it's moving fast, right? Its velocity at equilibrium is always what? It's going as fast as it can go. Its velocity is at a max. What's its acceleration at that equilibrium position? 0, because what's 0 at equilibrium? The restoring force. The acceleration is 0 because the restoring force is 0. Continues to go down to this point. As it's going this way, what's happening to the size of the restoring force? It's going up. But it's getting bigger in which direction? Up, right? So since the force is this way, but the velocity is that way, what starts to happen to the velocity? It starts to go down. Because if the force is this way, the acceleration is also that way, right? Whenever velocity and acceleration have opposite directions, we know that the thing's slowing. So eventually it slows to a stop down here. Down here we have maximum displacement. We have 0 velocity. But as soon as it stops, now what starts to happen? Now it starts to accelerate up at a maximum rate. Because what's also a maximum down here at the bottom? The size of the force, the restoring force. So we'll say the force is max. And that shoots that object back up. It goes through equilibrium. Right here, again, how much force is acting right there? None. But what's the velocity like right there? It's at a max. And so the velocity is this way, but as soon as it passes equilibrium, what starts acting that way? The acceleration and the force, the restoring force. Continues on up until it gets to a maximum displacement where it stops moving. Its velocity is 0. But now its acceleration becomes a max. Back down, because what else is a max right there? What else is a max up here? The acceleration is a max because what's a max? The force, the restoring force. And that restoring force is pushing that thing back here. That's mass on a spring, or what they might call a mass spring oscillator. One more thing you ought to know about it. Are you done? Just let it on. Is this equation. And this is one of the equations on your formula sheets. What have we said over and over again? Big T stands for emphasis most of the time. The period, the time for one oscillation. And in a mass spring oscillator, that period is really only dependent on what two things, according to this equation? What two things determine the period of a mass spring oscillator? Well, that's just 2 pi. The mass and what? The spring constant. How stiff the spring is. Those two things matter. If the mass goes up, what happens to the period? It goes up, which is where it's at in the equation, right? Bigger mass is going to make T be bigger. If the spring gets stiffer, if the spring constant is bigger, what happens to T? It gets smaller. That's what you need to know from here. That's a square root. No, that's just the dot. That's 2 pi m over k. I don't know why that dot's there. It's just a smudge. 2 pi times the square root of m over k. So that's the way a mass spring oscillator works. And we're going to work some problems with that here in just a second. The other thing we want to talk about, though, is the pendulum. Now, if you were paying attention to that first little video we watched, he said a pendulum is not exactly simple harmonic motion, but it's close. As long as what's really small. As long as this angle is really small, right here. The angle between equilibrium and your string. If you get out here, weird things start to happen, right? But if the angle is really small, I think in the video we said less than 10 degrees, we could pretty much call this simple harmonic motion. Which again means what's proportional to the displacement. To be simple harmonic motion, what has to be proportional to the displacement? The restoring force. And the restoring force is always which direction? Opposite of displacement, back toward equilibrium. So look at what we say here about the simple pendulum. Assume, number one, that the cord doesn't stretch and that the mass of the string is small enough to be ignored. Now, in reality, are either one of those things probably true? You know, sometimes we have to make trade-offs in physics so the math works. It's one of the trade-offs. The back and forth motion of our pendulum is pretty much simple harmonic motion. The restoring force is proportional to the displacement. And here's how we're going to find that restoring force. F equals negative mg sine theta. Now let's think about why that's the case. Now let me draw it up here for a second. So here's the equilibrium position. Here's our mass on the string. Here's our angle theta. If I went to this mass and I drew a line straight down, what would that line represent? The weight. Mg, right? That's mg. But what I want to do here is I want to break this weight into a component, one that's acting straight along the string, and one that's acting back toward what? Equilibrium. I want to break it into a component, two components, where this angle is going to be what? The same as this angle. So this is theta. Which one of my components is my restoring force? Yeah, this one right here, right? That's the one that's pushing it back to equilibrium. What would this component be? This component right here. Which way is that component acting? This component right here, which way is it acting? It's acting back that way. What's that going to do to the string? It's going to pull on the string. What do we call the force that's pulling on the string? Tension. That's the tension. So if we wanted to find the tension, how could we find that? This doesn't look like it, but that's a 90 right there. So how would we find the tension? If we know the weight, we know the weight of the object. So how are we going to find the tension? We could use cosine, right? We could say that. Let's just call this big T here. Did you say that?
Yeah.
No, I'm sorry. We could apparently deaf. We could say that the cosine of theta is equal to adjacent, which in our case is T, over hypotenuse, which in our case is mg. And we could find the tension. We could also find the restoring force, where that the restoring force is going to be equal to, we're going to have to use sine, right? We're going to say the sine of theta equals opposite over hypotenuse. And if we solve that out, I think you're going to see that this is what you get. Except we threw in the negative again to make it look like what? Why do we put the negative there? To make it look like whose law? Cooke's law. Where the negative just tells us that this force is opposite of what? The displacement. If we pull the pendulum to the right, the force is always going to be what? Back to the left. So if you want to find the restoring force, here's how you do it. If you want to find the tension in the rope, here's how you do it. Neither one very difficult to do. Just take your weight, divide it into one component along the string, and one component back toward equilibrium. In a pendulum, it only works for small angles, right? Less than 10 degrees. All right, now there's also an equation you need to know for pendulums, and this one's on your formula sheet as well. It's the period of a pendulum. Here's that equation. So the period of a pendulum is determined by what? Two things. What's L? The length of the string. And little g is what? Acceleration due to gravity. Those two things determine the period of your pendulum. What's not in there that you might think should be?
Weight.
The mass or weight of the string is not. And the mass or the weight of the object, right? Like the thing on the bob at the end, it doesn't matter. The only two things that matter for finding the period of a pendulum is the length of the string and the gravitational field, wherever you're at. And there's no need in knowing that formula right there. Because the only thing you have to do to get this is to do what? To this. Take the inverse. So I think that you can figure out that this equation for frequency is just 1 over 2 pi square root L over G. You can do a little simplifying to it, but essentially that's what you got. Period on the left, frequency on the right. Time for one cycle on the left. How many cycles per second on the right? What's the unit going to be for frequency most of the time? What's another name for how many cycles per second? Hertz. We might see that written as Hg, or Hz rather. We might see it written like that. But that just means something over seconds, right? Something per second. All right, so let's work a couple of problems. And I'm going to pause again here for a second. And I'm going to give back. All right, so this first problem off your packet that's related to pendulums or springs are problems 4 and 5. And if you look at those problems, it says a ball swings freely back and forth in an arc from point 1 to point 4, as shown above. Point 2 is the lowest point in the path. So point 2 right here, what can we call point 2? That's equilibrium. We'll put a big E here. Point 3 is located 0.5 meters above point 2. And point 4 is 1 meter above point 2. Air resistance is negligible. If the potential energy is 0 at point 2, why would the potential energy be 0 at point 2? How do we calculate potential energy? PE. Or your equation sheet is actually not using PE. What's your equation sheet using for potential energy? No, it's using a big U. That's potential energy. But it's equal to what? mgh. So why is potential energy 0 at E? No H, right? No height. 0 height. What's a maximum at point E? If our pendulum's going back and forth, what's a maximum at point E? The kinetic energy, right? It's going as fast as it can go at point E. As it goes up, what happens to the kinetic energy? As this pendulum swings this way, kinetic energy goes down because what goes down? What goes down as the pendulum swings up? Velocity. What's the equation for kinetic energy? One half mv squared. So the velocity goes down, kinetic energy goes down. But as the pendulum continues to swing up this way, what goes up? Potential energy, because the H gets bigger, right? So this is, what do we call potential and kinetic energies together? Mechanical energy. That's conserved. but potential may go up and kinetic may go down, or vice versa, depending on which way our pendulum is swinging. So this first question, if the potential energy is 0 at point 2, where will the kinetic and potential energies of the ball be equal? What's our answer? At point, right here, right at point 3, halfway between point 2 and point 4. At point 3, half the energy is going to be potential, and half the energy is going to be what? Kinetic. Make sense? At point 4, all the energy is going to be what? Potential. At point 2, right here, it's all what? It's all kinetic, but at this halfway point, it's half of each. All right, number 5 is a little tricky. Find the speed of the ball at point 2. Don't need too many numbers. Let's see how we would do it. The speed of the ball at point 2. How could we go about doing that? Anybody have any bright ideas? What you got? You want to? Yeah.
Point 3. So potential energy equals the kinetic energy at point 3?
Yes. It's halfway. So yeah, potential energy equals kinetic energy. The amount of energy in this pendulum is half potential and half kinetic at that point. Half and half. As we go this way, that potential is becoming bigger, the kinetic is becoming smaller. Until at this point, it's all potential, no kinetic. John Thompson, check.
Gravity is 9.8 per second. It says point 2 would be going in total distance 1 meter. That means it would be 9.8 meters per second.
Wait a minute, I don't get. You're looking for the speed? Is that what you're saying? You're trying to work number 5?
Yeah.
Hold that for just a second. Speed at point 2. Here's the thing. At point 4, up here, what did we have? At point 4, what did we have? Yeah, but what kind of energy do we have at point 4? All potential. And how much potential did we have at point 4? How much potential energy do we have at point 4? We don't know a numerical value, but we know it's equal to m times g times what?
Height.
What was the height? 1. That's the potential energy at point 4. At point 2, what's happened to all that potential? It's all become kinetic. So what I'm going to do is I'm going to say the potential at point 4 is equal to what? The potential at point 4 has to be equal to the kinetic at point 2. Dalton, you got a question?
Now, at what point does because the pendulum eventually will come to a rest?
Right, but if you look at this problem, it tells you to neglect air resistance and friction.
Yes.
So it never would.
We're not to neglect that. Where would it be? Kinetic energy was then less than potential, or the potential would be less than kinetic?
Depends on where you're at in the swing. They're both constantly getting less. So yeah, they're both going down. But here we're neglecting friction, we're neglecting air friction. So the potential energy at point 4 is going to be equal to the kinetic energy at point 2. Let's set the equations equal to each other. mg, and remember h was just what at point 4? 1 is equal to, what's our kinetic energy equation? 1/2 mv squared. What happens to the m's? They cancel. So right now we've got g times 1 is equal to 1/2 v squared. So let's multiply both sides by 2. Get rid of that half. Solve for v, so we take the square root of both sides. So v is equal to the square root of 2 times g. And if you plug that into your calculator, the square root of 19.6, 2g, is about 4.5. And actually, on these multiple choice, what are you supposed to use for g? 10. So 2 times 10, so 20. Take the square root of 20, you get 4.47, 4.5 meters per second. So your answer there is B. You didn't need the numbers. Does that make sense? Key thing to realize is the potential energy at your highest point is equal to your kinetic energy at equilibrium point. And you just set those two equations equal to each other. mgh equals 1/2 mv squared. All right, that one. Okay, number 11 is a spring problem. It has some tricks in it you don't know how to do yet. So you can X number 11 for right now. We'll get to 11 later. Don't worry about 11 just yet. Let's look at 21 would be the next one. '21 says a sphere of mass m1, which is attached to a spring, is displaced downward from its equilibrium position as shown above left and released from rest. A sphere of mass m2 is suspended from a length L, is displaced to the right as shown above and released from rest so that it swings with the pendulum with a small amplitude. Assume that both spheres undergo simple harmonic motion. The following is true for both spheres. Let's just go through the choices. If you look at choice A, the maximum kinetic energy is attained as the sphere passes through its equilibrium position. Is that true? Well, let's think. Up here, if this is at its highest point, what did we say this pendulum has at this point? All potential. But when it gets back to equilibrium, which is right here, what does it have? All kinetic. If the kinetic energy is at a maximum, what else has to be at a maximum at equilibrium? The speed. The velocity here in the pendulum is always at a max because the kinetic energy is at a max. Back to our spring. Let's say this down here is as far down as it stretches. That's the X max. This is equilibrium. When this thing shoots back up, what's happening to it as it's shooting back up? It's accelerating because there's what? There's a net force, a restoring force. When it gets to equilibrium, what happens to the force? It's gone. But what's the velocity like at equilibrium? It's at a maximum. So A is true. A is the answer. If you go through those others and you look at them point by point, none of the others are completely true. A is the only one that's true. At equilibrium, the velocity of any simple harmonic motion oscillator is going to be at a maximum at equilibrium. That's it. All right, the next set is 23 to 24. A block on a horizontal frictionless plane is attached to a spring, as shown above. The block oscillates along the x-axis with the simple harmonic motion of amplitude A. Which of the following statements about the block is true? So let's look. Right here, this is equilibrium, right? So at here, that's where x is out of whack. X is at a max. Over here, x would be at a max. Let's think about what we know. At x equals a max, what else do we know? At these 2 points that I have marked up in lines, for x is max, what else do we know? Velocity is 0, stops. Acceleration is a max here, and here it's going to be a max which way? To the right. Over here, acceleration is a max. To the left. What else is maxed out at these 2 points? The force. Does that make sense? In the middle, at the equilibrium point, we know x is what? At the equilibrium point, what's x? 0. What do we know about v at the equilibrium point? Max, right? What do we know about acceleration at the equilibrium point? It's 0, because what is also 0? The restoring force. So knowing that, let's look at our choices and see which one makes sense. Choice A, at x equals 0, its velocity is 0. Is that true? It's not true, it's at a max. At x equals 0, its acceleration is at a max. It's 0 there. That's not true. At x equals a, its displacement is at a maximum. That is true, right? At either x equals a or at x equals negative a, its displacement is at a maximum, right? What about D? At x equals a, its velocity is at a maximum. No, what's its velocity is at x equals a? 0. And at x equals a, its acceleration is 0. It's maximum at that point, right? So the only one that looks good here is C. C is your answer on number 23. 24. Which of the following statements about energy is correct? If you look at A, the potential energy of the spring is at a minimum at x equals 0. Is that true? At x equals 0, all the energy in that spring is what? It's all kinetic. So that is the answer. A is the answer. Where are the potential energies the highest at? X equals A and x equals negative A, right? What's the equation for the potential energy in spring? It's another one that's on your formula sheet. But the amount of energy, the elastic potential energy in a spring or in a pendulum, you can calculate U equals 1/2 kx squared. Where that the amount of energy is directly proportional to the stiffness of the spring and the displacement away from equilibrium. All right, so questions on 23 or 24? Yeah.
Why isn't it C?
On 24? All right, when it gets to the middle, this spring has been accelerated. Let's say the block started out here and it's moving back this way. When it's as far back as it'll go, its force is at a maximum that way, right?
Wait, I meant D's.
Okay, so let's look at D. The kinetic energy of the block is at a maximum. All right, okay. You can go with that.
I see what I did. I see it.
Yeah, at x equals a, what's at a maximum? The potential energy. It's not moving at x equals a, so it has no kinetic. It's okay. Any other questions about 23, 24? All right, this is the last set of questions. 29 to 30. 29 to 30 is again another horizontal oscillator, mass on a spring. It says, a block oscillates without friction at the end of a spring as shown above. The minimum and maximum lengths of the spring as it oscillates are respectively x minimum and x maximum. So here's our maximum displacements. Right here, that's equilibrium. This is x max, and this is negative x max, right here. Question says, the graphs below can represent quantities associated with the oscillation as functions of the length x of the spring. Which graph can represent the total mechanical energy of the block spring system as a function of x? Now think about something for a minute. What's mechanical energy? Potential and kinetic. This is a frictionless system. What's the right answer? E. Because what do we know about mechanical energy if there's no friction? If there's no friction, what do we know about the amount of mechanical energy? It's conserved, right? And the only one that shows that the total amount of energy stays the same the whole time is E. Now, question 30, you can't see on the screen right now. It says, which graph can represent the kinetic energy of the block as a function of x? So question E is not about the mechanical. Did you not have 30? All right, well, all 30 is, which graph can represent the kinetic energy of the block as a function of x? It's about that same graph. Same set of graphs. Well, let's look. At x equals max, what are the kinetic energies at x equals max? Either way, negative or positive? 0. But what's the kinetic energy at point E? It's at a max. So that's telling you it's got to be which or which? It's got to be C or D. Which one do you think it is? C or D? Turns out it's D. Most things in physics are quadratics, right? And what shape's a quadratic going to give you? A whole parabola. I mean, think about the equation for potential energy or the equation for kinetic energy. What are they both? 1/2 kx squared, 1/2 mv squared. Those are both what kind of functions? Quadratics. Quadratics always give you what shape? Parabola. So your best answer here is D. Does that make sense? When in doubt, look for a parabola. Physics is about parabolas. Does this make sense? All right. The other things that are on the test. Like I said, force problems. I'm not going to do much review on the force problems because I think most of you can do the force problems. But I want to do a couple more energy things. These are very similar, in some cases, just like energy problems off this packet that we already went over. But I want to go back over and do a refresher. So let's work this first one. An object of mass m is lifted at a constant velocity, a vertical distance of h in time t. What is the power supplied by the lifting force? All right, first of all, what's the equation for power? How do we find the power? Power is the rate of doing what? Work. What's work?
Force over distance.
Force, not force over distance. Force times distance, right? Yeah, that's okay. So that's kind of what we're looking for. So an object of mass m is lifted at a constant velocity, a vertical distance of h in a time t. What is the power supplied by the lifting force? If I take this remote control and I lift it at a nice constant velocity, how much vertical force am I applying to this remote? Equal but opposite to the weight, right? So the force I'm applying in this problem is what? mg, right? That's my force. So I'm working from this equation. The force I'm applying is mg. What's the distance I'm moving this thing? H. And how much time am I moving it in? Capital T. That's all I want. That's the power. I want you to notice something else. What's that? mgh is potential energy, right? Because what I've tried to stress to you as we're going through this unit, as you're doing work on something, what are you changing? The amount of energy that it has. As I do work lifting this object, the work that I'm putting in is turning into what? Potential energy. Remember that work is equal to the change in what? Potential plus kinetic. Work is equal to change in mechanical energy. And in this case, I'm moving at a constant velocity, so I'm not changing what? I'm moving at a constant velocity, I'm not changing what? If the velocity stays the same, what's not changing? The kinetic energy is not changing, right? Because kinetic energy is 1/2 mv squared. So not changing the kinetic. The only thing that is changing is the height, which means I'm changing what? The potential. Does that make sense? So that one should be an easy one. Let's go down to the next one. A person pushes a box across a horizontal surface at a constant speed of 0.5. The box has a mass of 40 kilograms, and the coefficient of sliding friction is 0.25. How much power is supplied to the box by the person? All right, here's the thing. You're pushing on this box, but I don't tell you what. What am I not telling you that it'd be nice to know? What do you got to know to find power? force. It's not telling you how hard you're pushing. But I am telling you that you're pushing the box so that the velocity is constant. Which means the force that I'm pushing this way, what I'll call my applied force, has to be equal but opposite to what? The amount of friction acting this way. And the nice thing about this problem is it gives us enough information to find the friction, right? Because what's friction equal to? What's the equation for friction? Mu times N. It gives us the mu, right? It gives us 0.25. So I'm going to say 0.25. It's on a nice horizontal surface, which means that N is going to be what? Equal opposite to the weight. Well, our weight is, we don't have the weight, but we have the mass, right? We got 40 kilograms. So let's say 40 times 9.8. Let's just use 10 for that now. So we'll say M times G. Let's multiply that out. 40 times 0.25. I'm going to go ahead and use 9.8 because that's what I'm used to using. And we end up with, that doesn't work out. Let me try that one more time. That comes up to be 98. So our frictional force is 98 newtons, which means we're pushing with a force of what? 98 newtons. Frictional force is going that way. We're pushing with an applied force going that way, 98 newtons. We know the force. We're trying to work from this equation. We're trying to find power. Power's work over time. Power's force times distance over time. But we don't know the distance or the time. But what do we know? We know distance over time is velocity. So the other way to write that equation is that power is equal to force times velocity. So essentially, in this problem, we're going to take our force, 98 newtons, times our velocity, 0.5 meters per second. Yeah.
So you know how you said that we can use that sheet on my feet?
Mm-hmm. Yep.
This sheet, or they're going to hand us one? Can we have
Yeah, they're going to give you one. It'll be just like that one, but they're going to give it to you. Can't have anything written on it. Well, what we'll do is we'll have a set of programs that we'll all share on our calculators. That way you won't have to have anything written down. Let's think about our units for this problem. We're calculating power. We've got a Newton times a meter over a second. What is that Newton times a meter? A joule. And what is a joule divided by a second? A watt. So our answer here, 49 watts of power. Does that make sense? All right, let's try number 3. Let me clear some of this mess out of the way first. All right, actually, there's 2 more problems I'd like to do today. Number 3 first. A blocks of mass M. Focus for me, guys. Slides over a horizontal frictionless surface table with an initial speed of v. It then compresses. Wait a minute. It then compresses the spring of force constant K and is brought to rest. How much is the spring compressed from its natural length? So here's the situation. You have like a wall or something with a spring, and you have a box that's sliding this way. And that box is going to hit the spring. What's the spring going to do to the box? It's going to start slowing it down until eventually it stops it, right? That box is moving. As it's moving, what does it have? What's a box that's moving across a horizontal frictionless table have? Kinetic energy, right? So that box has kinetic energy to begin with. But when it hits that spring, it starts to slow down, which means what's happening to its kinetic energy? It's going down. But its potential energy in the spring is going up, right? until eventually the box stops moving, and the spring is going to be compressed way down like that. At that point, the kinetic energy that the box started with should be equal to what? The potential energy in the spring. Everybody with me on that? The kinetic energy of the moving box is getting turned into potential energy in the spring. And what we're trying to find in this problem is the compression of the spring. So we're trying to find x, right? So what two equations are we going to set equal to each other? Potential energy of a spring is, potential energy of a spring, 1/2 kx squared. And we're going to set that equal to kinetic energy of the box, which is what? What's kinetic energy of anything?
Mass of acceleration.
1/2 mv squared. So we say potential energy of a spring equal to the kinetic energy of the box. Solve for x. So the halves, they cancel out. So we've got kx squared equals mv squared. We're trying to solve for x. So let's divide both sides by k. So that gives us x squared equals mv squared over k. And then we want to take the square root of both sides. So we got x equals the square root of mv squared over k, which for some reason the AP people like to take the square root of whatever you can. So they like to take the square root of the v squared. So they're going to write it this way: v times the square root of m over k. Either one of those would be right answers, though. Something I don't like about their notation, if you look at this problem on your sheet, they wrote the v over here. And it's really hard to tell if that v is under the radical or not. It's not. That's why if I was doing it, I would always write it in front. So it's obvious it's not under the radical. Does that make sense? All right, I want to go back to a problem or two that we've already done, but that aren't recorded. I'm going to switch PowerPoints here for a minute. All right, I want to work one or two of these problems real fast. Let's start off by doing, let's do number 2 off this list. A 75 kilogram bobsled is pushed along a horizontal surface by 2 athletes. After the bobsled is pushed a distance of 4.5 meters starting from rest, its speed is 6 meters per second. Find the magnitude of the net force acting on the bobsled. All right, let's think about this for a second. So let's think of our bobsled as a box, just to make it easy on my artistic abilities. We are pushing on this box. We don't know how hard we're pushing, right? That's what we're looking for. It's a frictionless surface, which means the amount of force that we're pushing with is equal to what? If it's a frictionless surface, we're assuming we're on ice, right? So essentially frictionless. The amount of force that we're pushing with is what kind of force? Since there's no friction, it's a net force. We push it, it starts at rest, so its initial velocity is 0. It ends up at a velocity of 6, final velocity of 6. And it goes from 0 to 6 at a distance, a displacement of 4.5 meters. And we're trying to find the net force. Now, one way of doing that is to go back to our old kinematic stuff, right? And what can we find with VO, V, and delta X? We can find an acceleration. Let's do that. We could use this equation. V squared equals VO squared plus 2A delta X. Solve that for 8. So if we solve that equation for X, we get V squared minus VO squared divided by 2 delta X equals 8. And then we can plug and trailer from that point. So if we do that, our V squared is 6. So 6 squared is going to be 36. We're going to have 36 minus our VO is 0 all over 2 times delta x. And in this problem, delta x was 4.5. So we're going to end up with 36 over 9. We're going to end up with an acceleration of what? 36 over 9 will give us, I think, 4, right? So we get A equals 4. We're trying to find the net force. So to do that, we need to go 4 times 75. So we're going to end up with 300 what? Newtons. We're looking for force, 300 newtons. Now, there's some other ways we could do this. And the other way we could do it is this. And this is really more the purpose of this unit. The big idea in this problem is we're doing some work on this box, right? We're applying a force over a certain distance. Just a second ago, we get through saying about work is equal to what? Force times distance, but what else is work equal to? Change in mechanical energy. Now, in problem 2, are we changing the potential energy at all? We're moving a box across a flat surface. Is that changing potential energy? What's not changing? What's not changing that would change the potential? The height. The height's not changing, so the potential energy is not changing. So in this problem, we could rewrite this. Since the potential and change in potential energy is 0, we could write work is equal to delta KE, right? And if we do a little manipulation of this, we could say, okay, I know work is force times what? Distance. We know the distance. It's 4.5. And that's equal to change in kinetic energy, which is, we started with 0 kinetic energy, right? The box started from rest. So the change in kinetic energy is whatever the final kinetic energy is at. And that's 1/2 times what? Mass, which we know, 75, times velocity squared, and our final velocity is 6. So times 6 meters per second squared. If you do the math on that, I think you're going to come up with 300. Okay? So 2 different ways to do the same problem. You can do work equals change in mechanical energy, or you can go do your old kinematic equations. Either way works. Same idea would apply to a problem, let's say like number 1. Problem 1, a student wearing frictionless inline skates on a horizontal surface. It's pushed by a friend with a constant force of 45 newtons. How far must the student be pushed, starting from rest, so that her final kinetic energy is 352 joules? Again, we could go and we could do a whole kinematic thing maybe to find this answer. But that's not necessary. We're doing work. We're not changing the height. This person's on nice flat ground, which means work is equal to change in what? Kinetic energy. We know work is force times distance. Do we know either one of those? We know the force, right? So we're going to plug in 45 newtons for the force. We're looking for the distance. We don't know that. But we know that this girl wasn't moving at first, right? So how much kinetic energy did she have to begin with? 0. But at the end, she has 352 joules, which means her change in kinetic energy was 352 joules. And just so we get our units right, what's a joule equal to? A joule is the same thing as a watt times a what? A newton times a meter. I'm going to write it that way, because to get my answer, I'm going to have to divide both sides by 45 newtons, right? And when I do that, 352 divided by 45 gives me a distance of about 7.82 meters. That make sense? Might as well go ahead and do number 3 while we're here. So number 3, a 2100 kilogram car starts from rest at the top of a driveway that is sloped at an angle of 20 degrees above the horizontal. So let's draw it. Here's our driveway. That's going to be our car. It's an angle of 20 degrees, so this angle is 20. An average friction force of 3,800 newtons impedes the car's motion so that the car's speed at the bottom of the driveway is 3.8 meters per second. What's the length of the driveway? 2 ways we could do this. Number 1, by the time it gets to the bottom, well, first of all, at the top of the driveway, what's the car have? It's got potential energy. How much? We don't really know, right? We don't really know. We know that to find potential energy, though, it's what times what times what? mgh. We know m, we know g, we don't know h, right? At the bottom, what's the car got? Kinetic energy. But does it have as much kinetic energy at the bottom as it had potential energy at the top? No. Why doesn't it in this problem? Because there's friction. And friction takes some of that energy and converts it to heat. So we can't say here potential energy equals kinetic energy, because it doesn't. We could say potential energy at the beginning equals what? We can say PE equals kinetic energy at the bottom plus what? Plus heat. And that would work. But have we learned how to calculate anything with heat just yet? No. So that's not going to help us, but that's a good statement of what? Yeah, but what's that saying? That's the law of what? Conservation of energy. First law of thermodynamics. You can't create energy. You can't destroy it, but you can what? What are the 2 words, the 2 T's? Transform or transfer. All right, so trying a strategy. What we know right now is we know that the car is starting at rest. It's got an initial velocity of 0. We know that it ends up at a speed of 3.8. We want to find the length of the driveway. Let's do it a kinematic way first. Kinematic equation first. We can go up here and draw what in first? What do we usually draw from the center of our box on an incline? The weight, straight down. And then what do we do to that weight? We break it into components. One component perpendicular to the plane, and one parallel to the plane. Where this angle right here is the same as that angle right there. So let's find our components real quick. We'll say the sine of 20 equals F parallel over the weight. And our weight is going to be 21 times 9.8, right? 2100 times 9.8. So that's 20,580. So let's take 20,580 times the sine of 20. And we end up with 7,038.8. All right, we really don't need the perpendicular component just yet. Because here's the thing. This parallel component is pushing that box this way, right? Perpendicular component, or the friction is pushing it that way. Which means we ought to be able to find what? We ought to be able to find a net force. The net force along the plane is going to be 7,038.8 what? What do we need to do with that 7,038.8? We need to subtract the friction from it, right? We've got 7,038.8 going this way, and we've got 3,800 going that way. So let's subtract them.
Could there be one like this where they didn't give us the friction?
There might be one where it's frictionless, but if not, they're going to have to give it to you. You're going to have to be able to calculate it, one or the other. They'll give you everything you need to calculate it. But the point being, in this problem, the net force is 3,238.8 newtons, the net force. We have a net force. We also have what? We have a mass. If we have a net force and a mass, we ought to be able to find what?
Acceleration.
An acceleration. And I'm not going to have time, I don't think, to finish this up. But here's the way you would do it. You would take F equals ma. We know F, we know m. Let's find A. We got an acceleration. We also know what other things that would help us find the length of this plane.
Where zero the force.
We know the initial velocity was what? 0. We know the final velocity was 3.8. So if you know an acceleration, an initial velocity and a final velocity, what equation would work nicely to find the length? You know v, v0, and a. You're looking for a delta x. The squared equation, right? V squared equals v naught squared plus 2a delta x. And you got it. So the test on Thursday, some force stuff, which I think most of you already know how to do. Several problems like the ones we worked here, either about springs and pendulums, or about work equals change in kinetic energy. There we go. And you guys watching the video, I will put up a link for you in a minute for the simple harmonic motion videos we watched at the beginning of class. All right, guys, for those of you who weren't in class today, the video for the simple harmonic motion video that we watched at the beginning of class is now on the screen. Make sure you take a minute and watch that video. It's about 8 to 10 minutes long. All right, good luck. See you on Thursday for the test.